Hello everyone, today we are going to understand what is backtracking. It is one of the most important topics to understand when you are trying to solve DSA questions or interview questions. It is also a prerequisite to understand the subsets DSA problem pattern. That pattern is really important because it is asked a lot in interview questions. So that makes backtracking essential to have in your arsenal. So the first question is, what exactly is backtracking? And backtracking is a very simple thing, guys. Backtracking is a simple recursive algorithm. So it means it's a simple recursive function that helps to explore all possible solutions of a particular problem. So basically, backtracking is used to explore all the possible solution of a particular problem. And it helps us to do that by allowing us to make different decision at each step. Now, this is the important part. What this means is that we can go through each and every solution of a particular problem by making different decisions. So by looking at the definition, it is very clear to us that we need to know what is a recursive algorithm. So if you do not know how recursion works or how recursive algorithms are written, this is the time to go ahead and watch some recursive algorithm videos, because backtracking is nothing more than a recursive algorithm. That's all it is. Most of the time, backtracking is explained like this. You are going in this direction, you made a change in the input, okay, and then you found an answer. Now, once you found the answer, you go back, you undo the change, and then you go into another direction. But this is not the way to explain it, because you are not really undoing anything. This word undo is a very confusing word, and to be honest, it is a very misleading word. What you are doing is you are making a decision. So what you are really doing is that you will be at a particular point in your execution, right? You will have some kind of input. Now you can do something with that input. You can add something in the input, you can remove something in the input, right? It's a decision that you are making. Suppose I decide to add one simple integer. Suppose that this is an integer like 8 and I decide to add 1. So it will become 9. And I pass this 9 into my recursive function in that particular spot. Okay. Now I find particular answer or find some kind of end result after the entire recursive function happens. And now I'm going back. And when I reach this particular point again, where I choose to add 1 in the input, now I can make another decision. I can make a decision that I do not want to add 1. Okay. I want to add nothing. Then that will actually just go in another direction, find another answer. Okay. And then we can also come back here. Okay. Now suppose this time I want to add 2. So I will add 2. 8 plus 2 is 10, right? So it will become 10. And 10 will be passed into another recursive function call, and that will return an answer. And then we will come back here, right? So this is what we are doing. We are making a decision. We are passing that decision into the recursive call somehow, and then that recursive call will eventually go ahead and get a result. And if we are not happy with that result, we can choose to make another decision. We are not really undoing anything here, right? Even if we had something like array, okay, we had 1, 2, and 3, and we decide to add 4 inside of it. So 4 will be here, and then we pass it into the recursive function call. It will get us an answer. Then we will come back. Okay. And now people say that we are going to undo this change. Okay. We added something in the array, and now we are going to undo this by popping the element. Well, do you really think you are undoing something? No, you're not really undoing something. You are just removing this element. Okay. And this element was never present in the array in the first place. So what you really did is that you made a decision to pass 4 in the array and then pass the entire array into the recursive function call. And once you get back answer, you are making another decision that, hey, I do not want 4 in the array. So I will pass a simple array 1, 2, 3, which was anyways the original array, right? So it's a decision whether you want to pass 4 or you do not want to pass 4. It's a simple decision. There is nothing undoing happening. It just so happens that you need to remove 4 by popping it from the list, and then you simply pass the list without 4 into the recursive function call. You can also pass some other element like 7, right? That is also a decision. So what you're doing is that you are making a decision, you're going through that decision, you get an answer somewhere here, you go back, you check if the answer is correct for you or not. If the answer is not correct, or if the answer is not to your liking, you basically change this input. You basically decide that you want to make another decision and then go through the entire recursive call again. And to represent this idea of making decisions, here is a simple template. So here we have our function, the recursive function, my recursive function, and we are passing an input. It can be an array, it can be a single integer, it can be an object, okay? It can be any input that we want to pass. Then here is the base case, okay? Since it is a recursive function, we will need to have some kind of base condition, otherwise it will go into a simple infinite loop, right? So here's the base condition, and here we can decide to do whatever we want. Whenever we hit a base condition, we can store the answer, or we can basically check the answer. If it is the correct answer, we simply return directly. Basically, we do something with the answer and we return. Okay. But if this condition is not hit, what do we have here? We are making a decision here. Okay. we have two recursive calls, one recursive call and second recursive call. So in this particular call, the decision one call, what we are doing is we have this particular input and we are adding a decision A. This decision A can be a simple number. We are adding 1 in the input. Okay. This decision A can be anything. So we are adding a decision A in the input and then we are calling this my recursive function. It will do something. Okay. We will end up storing an answer. We will end up getting an answer depending on the function implementation. If your function returns something like int or something, so decision one will store the answer. Otherwise, we are storing the answer anyways here in some other global variable, right? But at the end of the day, this function call will do something with this input and this decision A made. Okay. And after doing that, we will come back automatically. We don't have to come back manually. It will happen automatically. When the recursion will end, we will simply end up coming back to this particular line again. And so by now we have gone through the decision one. Okay. Now, depending on whether you like the decision one answer or not like the decision one answer, you can do multiple things. But here I'm just saying that, okay, you know what? I want to go through the decision one and I want to go through the decision two also mandatorily in every single recursive call. So I made the decision one. I went through the entire DFS call, got the answer, stored the answer somewhere in the global variable, and then came back. And now I'm going to make a decision two here. Okay. I'm going to use the same recursive function call and then I'm going to take the input and I'm going to make a decision B. The decision B can be some other number. Okay. It can be 2. It can be 0, whatever you want it to be. So we have a decision B, we add this to the input somehow, and then we basically perform this recursive call. Okay. This recursive call will go, will do something, will get an answer. That answer will also be stored in some kind of global variable. Okay. And we will come back. And this is basically what backtracking is. When you come back, okay, you make another decision on the next line. That's literally all backtracking is. You are not really undoing anything. You are just making a different decision. And sometimes you just have to remove an element from the array, or you have to just subtract something from the input. That's not undoing. That's just making a different decision. And that's it. And that's it. That is literally the backtracking that we have been afraid of for so long. It is nothing more than you making decisions and going in different direction, just like normal teenage people do. So in my experience, there are two cases where we need to use backtracking. First of all, when we want to find a particular solution. So it means we will have a lot of solutions for a particular problem. Some of them will be valid, some of them will not be, and we want to find a particular solution. There we can use backtracking because we can always make a different decision to arrive at a different solution. And then the second case is to find all the possible solution. So this is a kind of problem like subsets where you want to find all the subsets of a particular given array. So you will use backtracking for that also. And we are going to see both of these things in this video itself. First of all, let us try to go through this first case. Find a particular solution. So one of the best places to use backtracking is inside of a maze. You will have many different possible paths to go into and there can be many dead ends in the maze, right? So how do you represent a simple maze inside of a computer? You actually use 2D grid. That's all. So you will have this starting point, then you will have this wall. This W represents a wall or a dead end. And then this is the ending place or the ending cell. So you somehow want to go from start to end cell somehow. Okay. And this dot simply means that, okay, you can go into this direction. So how will you start solving this problem visually? Well, we can start from the starting point, right? We have this particular place and this is where we can start from. Now pay attention because now we are going to use a decision tree to actually understand how we are going to solve this problem. And decision trees are really important in backtracking. So this is how decision trees work. Okay. We are at a particular position that is the starting position. So this represents 0, 0 starting position. Now we can make a decision. We can go in this direction, right decision, or we can go in this direction, down decision. Okay. And let us place some constraint also in the problem. So you can either go right or you can go down. So these are the two constraints that we are placing on the problem. So I cannot go up and I cannot go left. Only right and only down. So here I have two decisions. I can go to this particular cell or I can go to this particular cell. So suppose I made a decision. Okay, now we are going for decision. I made a decision to go right. So it means I will end up in this cell. The coordinate of the cell is 0, 1, right? So I will be here, 0, 1. Now from here also I can go here or I can go here. Now if I decide to go right again, what will happen? I will come to this particular place, 0, 2, right? So I will be on 0, 2. But now I will see that, oh, it's a wall. So this W will be a string stored inside of this grid. Okay. So I will just check the string. Since it is a W, it means it's a wall. We cannot go anywhere else. We should not even be here, right? So it means we have hit a base condition and we will simply not go anywhere else here. Now the function call will automatically end and we will come back to the original choice, that is this particular cell. And this is the back part of backtracking word. Now we can go to this direction, the down direction. So I will make a decision and I will go here. So I made a decision to go on the down direction. Here we had right direction. Now what we will get here? Well, we will get this particular 1 comma 1, right? Because that is the middle cell. So I will be on 1 comma 1 cell and we will check what the value is on the cell. It is a W, right? It's also a dead end. So we cannot go anywhere else from here, right? So from here also we will go back. Okay, now it is a back part of backtracking. Now we are tracking back to the place where we made the decision to go down. And now that we have made both of these decisions, so this does not work, this does not work, right? So we will simply go back. Now we are going back to this particular original place. So we will simply go back to this particular original choice. This is where we made the decision to go to right, correct? And we are going back just because the recursive functions keep on ending. That's all. Now once we are on the 0, 0, we are basically back on the starting position. And now we can make a decision to go to the down direction. So I will go to the down direction here and I will get what? I will get 1, 0 because it is 1, 0 cell. So I have 1, 0 here. And now from here also I can go to down direction or I can go to this direction. Suppose I go to the right direction. So I have a line like this. I have right here and I will reach 1, 1 again. Now we know that it is a dead end. So we will simply backtrack. We will go back to the original choice and now we will try to go into different direction. So now we can go into the down direction and then we will reach where? We will reach 2, 0 and that is on the down direction. Now here also we have two choices. We can either go this side or we can go this side. Okay. Now if I try to go to the right from this place, I will reach the 2, 1 cell. Okay. And from here also you can go to the right or you can go to the down. If I go to right again, I will reach 2, 2. And here we see that E is written. E means end. So we have found the solution and we will simply backtrack and simply keep on backtracking and then keep on backtracking from here. We will get the result and we will store the result and send it back. Simple. But you might be asking that, okay, Satyam, this is fine and cool. But what if instead of going right, I would have gone down? What will happen? Well, simple. If you try to go down, you will hit another base condition that, hey, you are out of bounds. Okay. Out of bounds, and because of that you will again simply backtrack to this particular place and you will simply make the another choice of going right. Similarly here, if you try to go to the down here, you will again have to see out of bounds error and you will have to again go back to the original choice and you will have to make the choice to go right, and eventually you will reach this particular ending state and you will simply backtrack and go back to the original 0, 0 and you will simply return the answer. So this is the code for the problem that we discussed above. Here we just want to find out whether we can reach the end cell or not from the starting cell. So initially we are saying that we cannot reach the end cell. Result is false. Now we will try to use this function can reach end and we are going to pass the row and the column of the starting cell. In our case it would have been 0 and 0, but we should be able to start from any cell, so I'm using this row and column variables. Now here we are checking the out of bound conditions. If the row is greater than the number of rows present in the grid or the maze, we are simply saying return, it is out of bound. Otherwise, if the column is greater than the number of columns that are present in the grid, we are saying return, it is out of bound. Then here we are checking another base condition, that is, if the value at this particular row and column cell is W, that means a wall, we know that we have hit a dead end. We need to just return from here, right? Then here is another base condition in which we are saying that if we found the E on this particular row and column cell in the maze matrix, we can simply set the result to true and we will simply return from here. Simple as that. Simple. Here we actually got the result that we wanted to get, and that's why we are updating the result variable to true, so that we will simply return result variable as true as the answer. And here we are simply returning from the recursive call. Now if none of these base conditions are hitting, here are the lines where we are making the decisions for going right and for going down. So on this line, we are making a decision to go right. What will happen if I go to right first? That's why we are adding 1 to the column. In order to go to right, we need to add to the column. So this is basically where we are making a decision. We are adding 1 to the column, and that is a decision that we are making. And once we have made this decision, once we have gone on this particular path, we will get some answer, we will get a dead end, or we will have something. Okay, we will come back to this place. Okay, and now we can go to the other decision, that is going down. Okay, so for going down, we have to make a decision to add 1 to the row. So we have rows like 0, 1, 2, right? In order to go down, you need to add 1 to the row. And once you have made this decision, you will go in the direction, you will do something, you will get some answer, you will come back here, and this function will end. And once this entire recursive function runs, going through all the possible paths, we will know that we have found the result. Either it will be true or it will be false. It will remain false if in the maze we can never reach this ending position, because that's one of the cases that can happen for a maze. Maybe the point that you started from is actually an isolated point. There is nowhere to go from that point, so you will never reach the end. So we have discussed one of the use cases of backtracking where we need to get a particular solution from all the solutions or all the possibilities that we have from the question. Now we can move on to the next use case where we want to get all the possible solution of a particular problem. And to explain that, there is no problem better than the subsets problem. So in the next section, you will see me solving a particular LeetCode problem of subsets where we will go through the entire decision tree of how we can find all the subsets of a particular array.
Hello everyone, let's solve some LeetCode today. Today we have LeetCode 78, that is subsets problem. In this problem, we have been given a nums array that contains unique elements. It means we are not having any duplicate elements to skip. Now we have to return all the possible subsets from this particular array. What this simply means is that we have to return the power set of this array. The solution set must not contain any duplicate subset. Return the solution in any order. Here we have a simple array nums with 1, 2, 3 as elements to create a subset. As we can see here that we have a few subsets for this particular array. So what is a subset? A subset is nothing more than a collection of elements from the given array. For example, here we have the nums array as our input that contains 3 elements 1, 2 and 3, and here we have all the subset that we can generate from this particular array. So if we look at it here, we have a subset 1, 2. 1, 2 is actually nothing more than a simple collection of these particular 2 elements. In the same way we have 1, 3. So we have 1 and 3 as a collection in this particular subset. So that is what a subset is. You basically take a few elements from the array or take none of these elements from the array and create a new list, and that is simply a subset. And since we are taking elements from the array itself, the maximum length subset we can create is the array itself 1, 2, 3. So this particular array is a subset of itself also. Here are all the subsets for this particular array. Let us see how these are made. When we have 3 elements and we decide to choose none of them in our subset, we get an empty subset because it does not contain any elements. Now when we only try to choose one and remove these 2 particular elements from the subset, then we have only a single element in the subset, so we create a subset with element 1. The same way for 2. If we only choose 2 and remove all the other elements, we get another subset that only contains 2. In the same way, if we decide to choose 1 and 2 to contain in our subset and remove the 3, we get this particular subset 1, 2. In the same way, if we decide to remove 1 and 2 and only contain 3, we get another subset that only contains the element 3. In the same way, if we decide to take 1 and 3 in our subset and we remove the 2, we get a subset with elements 1 and 3. In the same way, we can decide to remove 1 and only contain 2 and 3 in the subset, so we get another subset that contains 2 and 3. In a similar way, we can decide to take all the elements from our nums array and then it will create the nums array itself again as a subset. So as you can see that we are just basically choosing an element, removing other element, choosing another element, removing another element, choosing a group of elements and then removing the other group of elements to create any subset that we want. In the question we can see that we have been explicitly told that the solution must not contain the duplicate set. So what is a duplicate set? Well, if we think about it, if I try to take 1 and 2 only in our subset, then it's a subset, right? But what about if I try to take 2 and 1? Are these 2 different subsets? Well, no, they are the same subset because they contain the same elements. So these are equal subsets. So that is why we are saying that if we have 1, 2 in our answer here, then we must not contain 2, 1. And we can see that here also. In this particular output also, we have 1, 2 as our subset. So it means we cannot have 2, 1 as another subset because that will be a duplicate. So how do we know that how many subsets we can create from a particular given array? And this is where the permutation and combination work. At each of these elements, we have 2 choices. We can either take it or we can either skip this element and we don't take it. The same way we can do for 2. We can take it and we can skip it. In the same way we can do for 3. We can take it or we can skip it. If we take 1, we skip 2 and we take 3, we get a subset of 1, 3. In the same way, if we take 1, we skip 2 and then we also skip 3, then we get 1, 2. In this way, we can create all the possible subsets. So we have 2 choices at each given index. It means the number of choices or the number of outcomes from these choices will be 2 multiply by 2 multiply by 2 is equals to 2 raised to the power 3. And as we can see that we have 3 elements in our array, 1, 2 and 3. It means the n or the length of this array is 3. So here we can say that the number of subsets will be equals to 2 raised to the power n, where n is the number of elements in the array. And so we have to figure out 2 raised to the power n subsets in our answer. Let us see how to create subset. Here we have an array with 1, 2 and 3 as elements. The index for these elements is 0, 1 and 2 respectively. Now at each index we know that we have a choice whether we can take that index or we can skip it. So that's exactly what we are going to do in our code also. So right now we are going to first of all create a decision tree. So the first index that I have is 0. I can either take this index or I can skip it. If I take it, then what will happen? I will have 1 here. If I skip it, my array will be nothing. It will be empty. Now let's move on to the next index, that is the index 1 or the element 2. I can decide to take this 2 or I can decide to not take this 2. And it will need to be decided on both these branches. So if I decide to take 2 on this branch, I will have 1, 2 as a subset. If I don't decide to take it, then I will again have just 1 in my array. Now here also I can decide to take 2. If I decide to take 2, I will have 2 in the array because it was an empty set. If I don't decide to take it, then I will again have an empty set here. In the same way, at each of these positions, I can decide whether I want to take 3 or I want to skip it. So if I decide to take 3 here, I will have 1, 2, 3 in my subset array, and if I do not take 3, I will only have 1, 2 in my subset array. In the same way, if I decide to take 3 here, I will have 1, 3. If I don't decide to take it here, I will again have only 1 as my subset. Here also, if I decide to take 3, I will have 2, 3. If I decide I don't want 3 here, then I will again have only 2 as my answer. Here also, in the empty subset, I can decide to take 3, then I will put it here. And if I decide I don't want 3, then I will simply again have an empty subset. Now we have gone through all the elements in our nums array. If we try to go further, we will reach the index 3 that does not exist in our nums array. So we can definitely stop the execution now. So we have figured out all the subsets of this given array. All these leaf nodes are representing the subsets. Now understand that this structure that you can see here is not actually a tree. So all these things are actually not a node. These are simple choices or decisions that we made throughout the execution of code. And these decisions eventually led us to these particular outcomes, all these outcomes. So this decision tree is basically a way for us to understand how our choices will affect the given output. Here we are choosing between taking 1 or not taking 1. Here we are choosing between taking 2 or not taking 2. Here we are choosing between taking 3 or not taking 3. So this is basically a visual representation for us programmers to understand how our choices are going to affect the particular input and the output. Now of course we are going to use DFS and backtracking to solve this particular problem. We can see that we are going to need recursion to solve this particular problem. So let us see how the recursion flow will work. First our code will be on 0th index. Then we will decide whether we want to take it or we don't want to take it. So suppose we decide we want to take it in the first line, then we will go here. So the recursion will go to this particular place. Remember that we are not touching this right now. Now in our subset array we only have 1. Now we move on to the next element and we see 2. Now we have to decide here whether we want to take 2 or not. So in our code we decide to take 2 and we will reach at this particular position. So we have 1 and 2 in our subset till now. Now we move on to the next one, that is 2, and we decide whether we want to take 3 or not. Then here we decide to take 3 and we have this particular subset. Now we will have a result array in which we are going to store a copy of these subsets. So suppose that this subset is called S1 and I'm storing this S1 here. Now the index will shift again and we see that we are out of bounds. So we will not go anywhere after this particular step, and since it is a recursion, this particular call will end and we will go back to this particular state. We can choose not to take 3 and we go to this particular branch. Now we are reaching the S2 subset. We only have 1, 2 subset, and if we try to further go to the next index, we see that we are going to get out of bound index. So we are going to get 3 here, so we can stop and we store the S2 subset also in the result array. Now the function call will end here and we will go back from this position back to the 1, 2 again. And here this entire thing is done. So we will go back to this particular state. Now we only have 1 in our subset, and here we go to the other path. We decide that we don't want to take 2. We go to this particular place. We have 1, and when we backtrack, we also change the index. So right now we are on index 1 here. Now at this particular position, we again move to the next index 2, and we decide whether we want to take 3 or not. If we decide to take 3, we will have another subset as 3. We will make a copy of this subset. We will store it here. Then we will go back because we will run out of indexes, and we will of course go back to the index number 2. And here we can decide that we don't want to take 3 elements, so we will go to this S4 set. We will now store this S4 set, and then we will go back to this particular position. The index is again 1. Now since this particular place is done, we will go back to this particular one. The index is again shifted here, and now from this particular one we go back to this particular 0th index. Now here we can actually actually go to the next branch, that is we decide that we don't want to take 1, that we don't want to take this first element. So we will go here, we have an empty element now because we did not take anything. Now the index is 1, we are at this particular position. Now we can decide whether we want to take 1 or not. So in the code, we are always taking the particular index in the first choice, and then we are coming back and neglecting it. So first in the code, we will take it. So we are taking the 2, and then the index will shift again. So now we are deciding between 3. We will take or not take 3. So first we will take the 3, and then we will get the S5. Then we will make a copy of S5. We will store it in the result array. Then we will go back. Then the index will also shift again. So index is not this anymore. So the index is now 1 again. Now we will take the another possibility, that is not taking 3. We will reach this particular subset as 6. We will make a copy of it. We will store it. Then we will go back to this particular one. The index will again change to first index. Right now this particular page is done. So we will go back to this particular index. So now we are back here. Now we go to the next possibility of not taking this particular element. So we again have an empty array. We did not take it. Now we can decide between this one. Now we decide to take it. Then we get this S7. Store here S7. Then we come back, and then we go to the next possibility, that is not taking it. So we again have this S8, that is empty set. Then we go back here. Since it is done, we go back here again. Then we again go back here, and now it is completely done. So this is basically how our result will be formed, and this is the result that we need to send back as answer. Now let's go through the code. First of all, I have defined the result array here, in which all the subsets will be stored. Then this is the function that will actually generate all the subsets. In this function, first of all, we are taking the index at which we are starting. Then we are taking a subset array in which the intermediate subsets will be stored. Since it is a recursion function, we have a base condition here. We are saying that whenever this source index will become greater than or equal to the length of this particular nums array, we know that we have gone out of bounds for this particular nums. So we have reached a particular subset. At that point, we are saying that okay, make a copy of this particular subset and store that into the result array and simply return, because there is nothing else to do after this index. If this condition is not true, it means that we are still in the middle process of creating the subset, and so we will go on. Here we are making a choice of taking it first and going in that direction. I will append the current element into the subset array, and then I will send this subset array into the next DFS call or the next recursive call for the next index. Now here I am deciding that okay, I don't want the current element. So yes, here I actually added the current element, right? So I will again have to remove this particular current element. So I will simply pop, and then I will send the subset. So right now this particular subset does not contain the current element, so it does not have it. And of course I'm passing the next index that I would like to make this choice on for both of these DFS calls. Now this entire function runs in the same way we discussed here, how the code will flow. And here I'm calling the function with start index as 0 and an empty subset array. We are going to add and remove the elements in this subset array within our code, and at the end we will simply make a copy of it and then append it in the rest. And here I'm simply returning the answer. One thing to notice is that I'm creating a copy of this subset array here. The reason is that when this particular DFS call will end and we will go back to a previous call, this subset array will change. Here we are actually popping the elements from this particular subset array, and the value in these functions are passed by reference, not by value. So it means that if I just say okay, append subset, not a copy, then this subset will change inside of our res array itself, and that is not what we want. We want to make a separate copy that will not change in our result array. So that is why we are making a copy and storing it in the result array. Now let's run it and see what happens. So it works. Beats 100% in 0 milliseconds. Don't trust LeetCode compiler. Now let us talk about the space and time complexities. We know that we are going to have to deal with 2 raised to the power n subsets. So anyways we will have to make 2 raised to the power n calls. It means that time complexity will anyways become 2 raised to the power n. The tricky part is space complexity. Usually people say that it is order of n, and they are somewhat right also, because they are talking about auxiliary space. Auxiliary space is basically a space used by recursion call stack. So yes, in case you are talking about recursion and its call stack, the space complexity is order of n. But if you are talking about the output array, the output array is basically a list of lists, and that is not order of n. So when we talk about output, we know that the output will contain 2 raised to the power n lists themselves, and each list will have an average size of n by 2. N is the number of elements in the given array. Why is the average size of list n by 2? It is because some lists will have 1 element, some lists will have 2 elements, some lists will have 3 elements, some lists will have 4 elements. Then at the end there will be a list that will will contain all elements. So when you take the average of sums of all these lists, you will get n by 2. So what we are saying is that we are going to store these many lists, and each list will have a size of n. So it means that I have a list of n by 2. I am storing it this number of times. So it will become 2 raised to the power n. So basically the space complexity will become n by 2 into 2 raised to the power n. And since we do not actually consider the constant stuff, we can say that order of 1 by 2 into n into 2 raised to the power n is simply equals to order of n into 2 raised to the power n. This is basically the total space complexity for the given output.
So if this video was helpful and you enjoyed it, just like the video, subscribe the channel, and you have some kind of question that you would like me to target, or you have some kind of topic that you would like me to talk about, just let me know in the comments. Now we will meet in the next video. Till then, bye.